Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. So for today's episode of the podcast, we've got Gavin White, who is the CEO and co-founder of a really interesting company that I found recently called About Energy. Gavin, welcome to the show.
Yeah, thank you very much, Ryan, for having me. It's a real honor to be part of the podcast.
Fantastic. So if you could just start off by introducing yourself to everyone, tell us about your background and, what got you into what you're doing now.
Yeah, definitely. Lucky this is a well-rehearsed script, giving it to a lot of venture capitalists at the moment. So that'll go down well. So I'm Gavin, one of the co-founders and the CEO of About Energy. My background was mechanical engineering, which I studied at Queen's University Belfast. Through university, I got the opportunity to do placements at Aston Martin. I was sponsored onto the engineering leadership program by them. So throughout university, I ended up doing, I think it was 18 months in total of placements.
All at Aston Martin?
Yeah, all at Aston Martin. I moved around department a few times, and the last 3 months were actually in the special projects and motorsport department. So that was working on the Valkyrie hypercar, which was like a collaboration between Aston Martin and Red Bull Racing, which was really cool. I'd say worked on it, but I think it's fair to say that I probably just observed what they were doing.
You watched the magic happen.
Yeah, exactly. Yeah, but that was very much like my dream job. And whenever I was doing it, I thought I should be loving this, really loving it. But for some reason, it wasn't really fulfilling me. And I realized it was kind of like the social cause wasn't really there in building these £2.5 million race cars for the super wealthy. So yeah, I had a bit of an existential crisis after university, went to Australia for a year, worked on a construction site in Brisbane, labouring, just building scaffolding, realised there that I didn't love labouring on a construction site either.
Quite extreme.
To no surprise, anybody that's met me would realise that I do not have the build for construction, especially labouring. But realised that I loved studying, and I also always want to start my own business. So I remember reading, as cringy as it is to say, Elon Musk's book, and in it he talks about, there's literally like 2 lines on it. He talks about how doing a PhD is a great way to start a company, because you get 3 or 4 years to really focus on the technology, and then that technology can form part of a company and a very defensible IP. So Elon Musk actually only did a PhD, I think, for 2 days before he dropped out. Moved to California with his brother. I didn't have the luxury of moving to California, so but his logic was very solid, and that kind of led me to start exploring PhD opportunities. So through many fortunate events, I ended up here at Imperial, and yeah, that was the start of my PhD, which was on developing fast thermal models for lithium-ion battery packs, which was sponsored by Rolls-Royce. Very early on into that PhD, I realized that the limitations weren't with the models, or it wasn't with the speed of the models, it was actually to do with the inputs. So stumbled across an invention for how to measure thermal conductivity more accurately. And that was literally just over 3 years ago, and spent a long time pursuing commercialization of that technology at Imperial. I was very fortunate, and probably a lot of the audience know Professor Greg Offer at Imperial. He was my supervisor.
Previous guest on the podcast.
Yes, that's right. Yeah, they can link back to that one. So he was very supportive of all of this, and then he linked me with the Fire Institution, and Neil Morris. He was there. So Neil Morris, he was the founding CEO of the Fire Institution, and at that point he had retired, but had came back as a commercial advisor, and that's when Greg introduced me to him. And that's where I got introduced to my co-founder, Kieran, from the University of Birmingham. So me and Kieran had never met, but we got introduced over this email chain with the context of, you're both working on good battery technology in very complementary areas. do you want to see if there's opportunity to start a commercial entity around the both of them? So I met Kieran a year and a half ago. And I guess, the rest is really history.
So Kieran, he wasn't at Imperial. He was at Imperial. Where was Kieran at again?
So Kieran was at the University of Birmingham. So he's like my doppelganger, but at the University of Birmingham. So the same way through our PhDs, worked on very similar like test measurements for batteries, but just in very different fields. It was kind of a very, very fortunate coming together, and luckily we were very compatible, like both in work and also socially. It's been like a very successful and fun time since then, spinning this company out.
That's a fantastic story. And I mean, I don't know. I mean, I wouldn't have normally made that connection, doing a PhD and then immediately setting a company up, sort of deep science. But it's a very good point that you make in terms of doing that. And obviously, big advantage in terms of the network that you built straight away through the different people that you were exposed to. So you've kind of, you ended up immediately reaching beyond Imperial to Birmingham to a much broader group. So what is it that that you guys are doing about energy? Why did you set the company up?
Yeah, so we set the company up because, I guess myself and Kieran, we both stumbled across these measurement techniques for measuring batteries more accurately than anybody else. And I guess the real problem that industry is facing and society is facing is that a lot of battery development at the moment is done through trial and error. I think, definitely I still find it unbelievable that we use batteries in everything from our watches to mobile phones to like electric cars, grid energy storage. But it's quite unbelievable how little is still understood about the battery and how it works and how to design systems. And a lot of the development of these products is just done through trial and error. So you look at cell manufacturing, and a huge amount of cell manufacturing is literally just people throwing materials together, mixing it up, and then just churning out batteries and testing them. And the reason that is because they don't trust the models such as they do in other engineering disciplines. Like I came from a mechanical engineering background, and in our university course, as I'm sure many of your listeners could relate to, you do computer-aided engineering such as CFD, computational fluid dynamics, as well as strength of materials, where you do optimization of, say, like a metal block in order to reduce its weight and improve its strength. And these models are very well established and the results are heavily trusted. The same cannot be said for battery models. And that's really the problem we're trying to address, is we're trying to take these battery models that exist and make them more accurate.
And is it, why do you think that is? Is it because they're cross-domain, like electrochemical, thermal? You got some like fluidic stuff going on as well. What is it? Is that complexity of, I think is multi-physics is the correct terminology, something like that? Is that it? Or is it just because it's not, I was going to say because it's all new, but it's not really, like you say, battery cells in all sorts of things for years and years and years. So
I think it's the complexity of what's really going on. Like even the most in detailed, what we call physics-based electrochemical models. There's like a very famous one, the Doyle-Thurn-Newman model. Even that model makes so many assumptions about what's going on inside the battery, how the lithium is deintercalating, how it's been transported across the separator through the electrolyte and then being reintercalated. Even these models make so many assumptions of that very, very, very complex chemical diffusion process. So the reality is the models aren't perfect, and they're also very, very difficult to parameterize, to measure. Like this stuff's going on at kind of like the nanometer resolution. And you can't put a test probe in to measure and contextualize what's going on because you would interrupt the process. So batteries are kind of like this mythical little box where you put current in and out. And the only thing you get out the other side is the voltage response, and you can measure the temperature of how much it heats up. And literally everything else you have to work backwards to try and figure out the processes. So I think one day they will get there, but right now we've identified that they're limited by the inputs that go into the models. The models still have a long way to go themselves, but is what we're really trying to do is help companies digitalize a lot of their R&D and use computer-aided engineering to reduce cost and time to market.
Okay, cool. So you basically, through your work and the things you were doing, you sort of realized the existing models had limitations, and you came up with a better way of doing it, and now you're helping other people apply that better way. I mean, do you just do that, or do you also do sort of more conventional like battery analysis and things like that, or are you more sort of focused on that improved modeling technique?
Yeah, so the way it kind of works at the moment is we have like two types of revenue streams and customers. We have one which is the consultancy, which we call more of a technical partnership. So it's between us and the clients, and we offer them a lot of advice, support. We advise them on what's the best models for the challenges they're trying to address, and then in that they can send us cells under NDA, and we can test them, keep all that information secret and proprietary. And that's more of a kind of recurring services consultancy contract. And then the other part, which is the far more scalable part of the business, which is where we're going to have the biggest impact, is on our kind of SaaS products, so software as a service. And that's where we buy commercially available cells. So these are batteries that literally anybody could just go and buy on a website right now from Samsung, LG, Panasonic, Sony. And each of these manufacturers has like 8 to 10 different cells available at any one time, different makes and models, similar to, I guess, different like car models. So some of the batteries are optimized for cost, some are energy, some are power, some are degradation. You can't have all of them. It's impossible. So is what these manufacturers do is they place different models and makes in these kind of different areas. So is what we do is we buy each of them batteries, we build models of them. And then we provide these models as a software as a service to companies that are trying to develop battery products. So these kind of batteries are used in things like your electric scooters, your electric bicycles. Actually, a lot of production electric vehicles use these batteries. So unless you're building hundreds of thousands of electric cars, you don't get the economies of scale for your own custom chemistry. So a lot of it's done on commercially available cells.
Interesting. And is that your model? Is that used to help the primarily at design stage, or would people actually also use that in terms of like their BMS and sort of controlling the life of a battery pack?
Yes, we very uniquely, and this is why the two universities were brought together. We very uniquely offer a range of models for a range of different problems. So we have like very detailed thermal models, electrical models, electrochemical models, and degradation models. And you need each of these models through the different like journey or life cycle of kind of a battery product. So a cell manufacturer would need electrochemical models to help them design and optimize the chemistry in the cell and how that's packaged into the form factor of a cell. And then say an automotive design team will first need to select which batteries of it, is the best for their application in the market. So they probably need an electrical model in something like Simulink, so they can very quickly prototype lots of different designs. Then that kind of moves over to the actual integration team. So that team will probably need electrical, thermal, maybe even electrochemical models to actually design the thermal management system and the battery pack. And then you go over to the control team, who then have to control how you charge and discharge this battery and monitor its state of health. So then you're over to electrochemical models, electrical models. So there's no one model for one area, but we very uniquely have expertise in all the different areas, the key areas of battery modeling. And it's what we're doing right now and still developing is products and services that, help each of these key areas of battery development. So if you're like selecting a cell per application, we're developing a product that will help you narrow down, the 500 to 1,000 cells on the market and work out, well, what's the right one for your application.
Okay. So almost like the reverse. So not you can help someone look at a specific cell and kind of model that and understand how it's going to work. But then the kind of reverse of that, you can look at an application and help to sort of down select the appropriate cell for the application. Have I understood that correctly?
Yeah, exactly. So we basically have an algorithm that basically hunts through all the different commercially available cells. And this is still something we're developing. And then it helps you shortlist. So it doesn't say, oh, this is the best one for you, because in reality, the application is so nuanced. It's very, very complex. But it says, here's where you should start looking. like Samsung have this very interesting cell, LG have this interesting cell. Maybe these are the two you should be looking at. And the platform we're developing is called the Voltt, and we're actually having the public launch of it mid-March. Is actually going to have all this data on it and have this algorithm. So you can very quickly go onto this platform, view all the cells in the database, run this algorithm, see what's the best cells for your application. But it's not just the technical performance of the cells, it's also like the techno-economics, like supply chain sustainability as well. Like what materials are in that cell, how much cobalt, how much manganese, where's that cell came from, like how much carbon is embodied. So we're working with partners because we collect a lot of the raw data through our teardown procedures as to like what's stored inside the cell. And through third parties, we're going to have plugins which help analyze the supply chain and the ESG of themselves.
So you wouldn't be just relying on, because I know some of the cell manufacturers produce these kind of certificates of provenance that, in terms of where the raw materials came from and that it's no child labor was used, etc. But so you're not just relying on that; you're actually basing it on teardown analysis and actually looking deep inside.
Yeah, exactly. We're setting ourselves up as like the independent kind of test facility for battery selection. So cell manufacturers publish some data. They have data sheets that supply kind of like voltage traces over different current ranges. But the problem is you don't know what conditions that cell was cycled under. You don't know what battery cycler that was on. Every battery cycler has a slightly different calibration. So we want to standardize, harmonize. Really, we just want to enable people to build battery products. That's kind of our mission, and accelerate kind of our transition to electrification.
Interesting. And of your the companies that you're working with, is it mainly battery cell users or is it cell developers? Like which where do you sort of fall in the supply chain?
Yeah, we've been super fortunate last summer, kind of when we were going around speaking to lots of companies, seeing if there was demand for this kind of service. We realized that demand was going to outstrip supply. So we were very fortunate to be in a position that we could be very targeted about who we work with. So we chose, very specifically, a material developer, like an electrode manufacturer. We chose a cell manufacturer, an automotive OEM, and a motorsports company. And the goal was, in them projects, we would learn how to map our technology to their needs and develop these products and services. Because as I'm sure you can imagine, every like area of that industry has different needs. They will have different criteria to assess performance. So that's been really good over the last 6 to 9 months, is taking that learning, which has enabled our future product development, which will help us expand in the future.
Interesting. Right across the supply chain, really, sort of active materials, cells, up to end users. That's interesting that what you do is kind of brings value right up the supply chain. It's fantastic. Well done.
Well, thanks. To be honest, it's just very fortunate I came along at the right time. There was all this technology at Imperial and the University of Birmingham, and I stumbled across that invention. So I think it's just the right place at the right time. Everybody says you have to get lucky in business, but I did not really believe how lucky I would get in this opportunity.
Well, I think you've been very humble. You create your luck as well in terms of having your ears and eyes open.
Yeah, I'm sure you know yourself from your experiences. It's
a bit of luck. I just wanting to kind of circle back because it's a topic of real interest. I mean, in a few different ways, like the trying to kind of unpack what you do, but I think because like if we started with what's going on in a cell, and you made a comment earlier about you can't have power, energy, something else. There's sort of like 3 or 4 different performance characteristics that you rattled off. If you were thinking about it at a cell level, what in a nutshell, why is that? So what drives these differences in the different kinds of cells and the performance that you can get out of them?
Yeah, definitely. So I think people always wonder this. They're like, how is there not one battery which just does everything, meets all the requirements? But the reality is it's like very nuanced in the design as to, why certain cells are better for certain applications than others. So for example, there's a very clear trade-off between energy density and power availability. To get more power, you add more aluminium and copper into your current collectors, which allow you to extract the heat and also move the energy out of the cell. But obviously by adding in the aluminium and copper, they're not the active materials that are contributing towards, the energy storage. So you're reducing your energy density. And the similar trade-off can be made between cost and degradation. For example, it's much more complex than this, but to oversimplify it, if you want to extend the batch, like the lifetime of your cell to improve how many cycles it's going to last, you might add in, more exotic materials such as cobalt. Cobalt's like very, very stable, and it keeps the battery for a long lifetime, but it's also very, very expensive and has all the supply chain issues. So if you want to make cheap batteries, you can't really use cobalt, but then your cells aren't going to last as long. And the same applies for other, material variants, whereas the more expensive ones tend to last much longer. So you kind of have this trade-off. So there's more dimensions than, the four I mentioned, but like that's how complex it gets. And that's why these manufacturers have like a broad range of cells available. But to like, even to me, who kind of understands high level, what's going on in the cell, if I was to design an electric scooter, even I would really struggle to understand what's the best cell for that application. Reality is at the moment, you have no choice but to build lots of variants, buy lots of cells, do lots of real world tests, and then just see which was the best one. Whereas our goal and our aim is to produce the most representative models to help digitalize that.
It is difficult, I guess, particularly with as well a lot of the supply chain restrictions, because a big variable can be like almost what can I get, as much as who wants to play nicely this week with the cell guys. It seems to go in cycles of them wanting to be in new projects and then not. So there's a bit of activity there. You I'm going to pick you up on you mentioned about cobalt in particular, and that just sort of sparked a question for me, because that's a huge topic, and you make an interesting point about typically cobalt's been used to stabilize and to sort of extend the life cycle. So one of the things, the NMC sort of cell chemistries, they were sort of revelation when they came about because of the step up in energy density actually and power and extending the cycle life compared to what had been in the market for such a long time. But now we hear people are aiming to try and eliminate cobalt. Elon Musk in particular has been quite vocal about getting rid of cobalt. It can't be that simple, surely. How will that be achieved? Is it by going to sort of more exotic, high silicon? How can we get rid of cobalt?
Yeah, I think cobalt's the one that everybody's aware of because of obviously like the supply chain, the kind of child labor used in some of the...
Makes for good newspaper articles.
It does, but it's not the only problem child in kind of battery materials. So you have nickel now as the latest one. Yeah, I think it was like this time last year, there was the crazy Russian nickel where it went up by 2,000% in a day. And the London Metal Exchange like halted trading, which I guess you could argue is kind of fraudulently. So people are even trying to move away from nickel at the moment. I'm no expert in material chemistries, electrochemistry as to, what chemistry is going to dominate in the future. But there's definitely a huge shift back towards LFP.
Yeah.
So that's lithium iron phosphate. And I would say back because it's been around for a long time, but it was always kind of written off as it wasn't very energy dense. It's like you say, these new exciting chemistries came along like NMC. But now LFP in the background has really caught up, which has really been driven by CATL in China.
So I was going to ask, is because it LiFePO4, was LFP is so much easier to say. It was like a proper staple back in the day, like the first battery pack I ever built. It was LFP prismatics from a certain supplier.
You were ahead of the trend. You were 20 years ahead. You didn't realize at the time.
Well, clearly not. I do remember them being quite troublesome, and cell-to-cell variation was pretty horrendous as well. So there's certain characteristics of the cells were quite hard to deal with. And is that just because they were not being made very well and someone's kind of got the recipe right, or has there been some like fundamental, improvement in LFP technology? What's caused that?
I honestly wish I knew. I have absolutely no idea what's. But yeah, there's obviously been like huge investment in LFP, improving a lot of this kind of variance and mainly in the energy density as well. But LFP still has its challenges, which are being addressed. Like there's the kind of voltage hysteresis, which is basically if you were to charge, I don't know if you remember, you probably struggled over this at the time, when you charge and discharge the cell, you get a different open circuit voltage. And why that matters is because your whole battery management system uses this as like its reference point. So you have this thing that's changing, and it makes it very, very difficult to estimate state of charge. And it's literally, the problem is as big as, I don't know if I have 20% like state of charge or if I'm at 40%. Like there's this huge, huge uncertainty.
And it badly affected by temperature as well. If I recall, it seemed to get, if you started to push it towards the corners of the operating temperature envelope, it got quite extreme. And it's such a flat curve anyway, So for people who aren't familiar with this, what we're rabbiting on about here is when you discharge a lithium-ion battery cell, you go from its sort of full voltage to its empty voltage, and its empty voltage isn't zero; it's still a reference voltage. You can't completely discharge a lithium cell without damaging it, and old-fashioned batteries have a nice big difference between when they're full and when they're empty, and a nice straight line in between the 2 points roughly. So it's quite easy to tell if the cell's full or half or quarter or 10%. But lithium-ion cells have a much smaller delta between the full and the empty point for the cell, or the minimum voltage you can take it down to. And the line in between the two is not straight. It's a kind of an S. Yeah. So you've got to, this is partly, I guess, where a lot of your models and things come in useful, because it's very, very difficult to then, in the life of the pack, you've got to do two things so you're looking at that cell voltage with the battery management electronics. And one of the things you're trying to do is tell, it's a fuel gauge. So I want to know how much energy I've got in my battery pack. So that's fine. But the other thing you're trying to do, the pack performance changes slightly over its life, and it changes, like those points will change with temperatures. So you're also trying to get a state of health as well, reading. So it's very, very important, this kind of charge and discharge curve. And Gavin's point there was that the charge discharge curves are different. They call it hysteresis, but it's like literally trying to pin the tail on a moving donkey, trying to work out where that cell is, and compensating for temperature and compensating for degradation in the life of the cell. It's quite an interesting challenge, but it is, because to be honest, I never thought that LFP cells would be suitable for kind of high volume automotive.
Yeah, I don't think anybody's seen it coming, did they? The last 5 years, they've really taken the market by storm.
Yeah. So you've got LFP is very common in China, even Tesla using it in some cars in China. I think where it partly helps some of the disadvantages with LFP in terms of packaging the battery packs, so the lack of sort of volumetric energy density. So these things are bigger. But if you've got a vehicle that was designed to be electric from the beginning, you tend to have plenty of space to fit the battery. So the sort of vehicle design has evolved to the point where some of the limitations aren't as important, but all of the other limitations still exist. So hats off to the people who are making these things work. I do wonder if cattle have just sort of got the consistency better, that kind of material blend, active material, sort of consistency, the manufacturing methodologies, is, if you've ever been to a battery manufacturing plant, it is quite amazing, actually. And we take it for granted. But it's like, I don't know, it's quite hard to explain. You're suited and booted, and it's kind of a controlled atmosphere and a sort of very, very high standard of cleanliness. And when I say suited and booted, I don't mean kind of in your business suits. It's sort of clean room equipment.
In your hazmat suit. It's more like that.
Yeah, hazmat suit, exactly. So very, very kind of controlled manufacturing environment, but then the processing, millions of cells, so there's materials and stuff whizzing all over the place, and then these huge kind of crypt-like structures where they bring the cells to life like Frankenstein.
Yeah, lots of things spinning around. I'm sure everybody's seen the kind of Tesla promo videos of the 4680 production line where you have cells the craziest thing is you watch that video and then you learn afterwards that was it in slow motion. It's incredible.
Yeah, a bit like millions and millions of units of production, and the sort of reel-to-reel processes, so big reels of stuff whizzing around, which is it's fascinating to watch. LFP is sort of seeing a surge. Cobalt reduction, we touched on. You mentioned nickel. Because of some of the issues there, nickel reduction. What else, obviously you're not giving away any secrets of your customers, but what else do you see in general in the market in terms of a trend with what people are doing with battery cells and battery packs and cell development and pack development and things like that? What's your perspective on where the market's going?
Yeah, well, from a modeling perspective, there's definitely a shift towards more physics-based electrochemical models. Like traditionally, is what's used as an equivalent circuit model. And to explain an equivalent circuit model very, very briefly is it's kind of like a black box solution. So you just treat your battery as this black box where you charge and discharge it and you get some voltage response. And then you take some very, very primitive circuit elements, such as a voltage reference, a resistor, and then a couple of capacitor resistance pairs to kind of get the time dependence. And then you just mathematically fit these circuit elements to the voltage response. And that's what's running in your mobile phone right now, in your smartwatch, your laptop. That model is used backwards to work out the state of charge, like how much energy is available for you to use. And these models have been used, for the last 10, 20 years to design control systems. But now there's definitely more of a focus on going down one level deeper, trying to get more understanding. It's like not a full black box solution. We've definitely seen huge demand to understand what's going on inside the cell, because there's a lot of very complex things happen that these kind of black box models don't explain. So like my supervisor, Greg, has been pioneering these kind of like equivalent circuit, these distributed models to try and capture the non-uniform current flow within a single cell, non-uniform heat generation, state of charge within a single cell. Because that's another thing. Within a battery, the whole battery isn't at a uniform state of charge. Different areas of the battery are a slightly different state of charge and they have different current flow. And then you map that over a whole system like an electric vehicle. And the problem just gets so complicated. You add in bus bar resistances between the cells. So is what we've directly seen is that people have built battery systems, built battery cells, and they haven't performed as they expected. And the question now is why? And that's where we're really kind of helping them open the door and see, look inside the battery to see what's going on. And there's like a whole spectrum of models. Everybody always assumes that there's like this kind of gold standard pinnacle equivalent or electrochemical model that can explain everything. Most people don't realize that even that, the kind of Doyle for a Newman model, is built on so many assumptions, but often that's kind of overkill for what somebody needs. So we're helping them join the dots by learning from them, what insights do you want to glean, so that we can advise you on what's the best most representative, most accurate model for your specific application.
Ultimately, how that manifests itself today is people, like we've sort of seen, several manufacturers launch electric vehicles and have basically quite big batteries, but with much lower usable capacity than others. So they're putting like big operating headroom on the battery. A lot of the reason for doing that is effectively kind of building in a buffer to make sure that they don't get caught out in the life of the vehicle with unexpected degradation or performance change or some sort of issue. So they've kind of they're not kind of prepared to take the risk of running on that knife edge, because it's like, we're not really confident in what's happening. So building on your work and the things you do would allow the manufacturer to more finely optimize the pack, and the cell usage, and basically get much closer between the predicted performance and the actual performance, and then take out some of that headroom and sort of excess capacity and get much closer. So smaller, lighter battery pack to go further, ultimately.
Yeah, exactly. So it's in the upfront design, so they can optimize the system to reduce the mass, the cost, the size of the battery pack, remove or reduce like this extra headroom that you're talking about. But then also now a lot of electric vehicles come as standard with over-the-air updates, which is really pioneered by Tesla. But the key thing with that is it allows you to update the control algorithms that control the battery through the lifetime. Because whenever the life cycle for the development of a car is, 5 to 7 years for large auto manufacturers, and that's the whole way from concept down to, the first cars running off the production line. But batteries, are expected to last 8 to 12 years. So even on day one of you coming up with a concept for a car, if you selected your battery of choice, by the time that car is on the production line, you only have 4 years of degradation data. So you actually haven't, you don't know how long that car is going to last. So what happens is, the automotive companies are running these degradation experiments a few years, 2 or 3 years ahead of the cars being out in the market. And then they take them insights and them updates, and then they can update the battery management system actually on the vehicle in real time to account for it.
Yeah, so before Tesla, it's pretty much unheard of for people to use over-the-air updates or data gathering from the customer's vehicle in the field. And a lot of people in automotive would have looked down their noses a bit at that in terms of, the customer's not a test pilot. But actually, it's impossible to recreate such extensive data in such a short time. In the past, with more conventional vehicles, OEMs always looked at warranty data and field failures and things like that. But this is a new kind of era where obviously the problem with the field failures is it only tells you about something once it's critically failed, rather than giving you live analysis and predictions and things like that. So gathering data from vehicles in operation from your customers is really, like, I think that's going to be a big trend into the future. Do you think that manufacturers will start to use that to improve the design of battery packs, battery cells? Or do you not think it will get that kind of joined up?
Yeah, absolutely. So these automotive companies are already using this. There's lots of third parties that help them take this raw data from their vehicles and process it online and produce some sort of meaningful analysis and results. There's definitely going to be a trend of these automotive companies using this to work out what they can improve in the future. And we think we have a key part to play in all of that. So we would supply models to these third parties or to the automotive companies themselves that allows them to go from this raw data, which is like their CAN bus signals of voltage and temperature traces, and kind of work that backwards into, well, what was actually going on in the battery at that moment? And can we use this insight of knowing what was going on in the battery in that moment, spread over these huge data sets to build some insights into, under these conditions, we're likely to see very high degradation, or under these conditions, the batteries are running at optimal performance. And these are the kind of insights that for future products, but also for over-the-air updates, you can, recalibrate your control mechanisms. And they can be very, very minor updates, as in slightly change the charge protocol, or when a consumer requests power, slightly change how much is available or the ramp rate. of the cells. But that can be enough to really add significant amounts of time onto the battery lifetime, whether that be a year or a few years, to meet the warranty obligations.
That's a lot of where it gets very complicated in automotive compared to other applications like consumer electronics, where it has to last 12 months and then you're done. But automotive is very harsh operating conditions everywhere in the world with long warranties, 5 years, not untypical, typically longer even sometimes. So yeah, it's very, very difficult engineering vehicles and products that go into vehicles. So all of that data is going to be very, very helpful for people into the future. And I mean, you've kind of answered this along the way, but just to sort of wrap things up a bit, what is it that About Energy is going to be doing? Like, what are your plans for the business, and what are you planning to do in the near future?
Yeah, definitely. So we've only been trading as a company now for 10 months, which is actually kind of scary. Thinking this time last year, we were still trying to spin out the universities, getting our license agreement sorted. And yeah, we got our first contracts in January, February, and our first investment in April. And that allowed us to commit to our first full-time employees. And we went from 0 in April to now 12 full-time. So now we're actually in the process of raising some more money, which will allow us to build our own lab facility in London, as well as commit to hiring a few more people. And then it's going to be a real focus on our product and our technology, and packaging that up into something that's usable for the battery industry. And like I said earlier, we're launching what we're calling the Voltt, which is our web platform. And on that platform, there'll be loads of battery information, like all the cells, kind of a lot of the information scraped from their data sheets. But then on specific cells, the most interesting cells, we're actually doing a lot of testing, and we're going to have models within them. So hopefully in the future, About Energy's, well, our brand, our profile is going to be heavily raised by this. And I think your listeners will probably be glad to hear we want to open up a freemium kind of model.
Okay, I was going to ask how it's going to, the Voltt, whether that was going to be a subscription thing, or how you're going to go about doing that. So freemium.
Freemium, I think, is what they call it in the business world, yes. But you'll be glad to hear it. It would feel cruel to tell you about all this cool stuff we're developing, but then you'd never be able to see it. So...
Well, it depends, doesn't it? Not necessarily. You've got to make a living out of these things. So people presumably will be able to get some of this for free, but then pay an additional amount to get more detail and all the sort of in-depth stuff behind that.
Yeah, exactly. So it'll be a business-to-business web platform, but we know that people have so much interest in batteries, so many students out there. So we will kind of want to open it up to get their input, and also to educate them. I think there's a lot to be learned on batteries. There's, I'm sure you know, a massive skill shortage. Companies are scrambling to hire top graduates. I can't remember, somebody was telling me a few weeks ago that like the average battery engineer just lasts like 12 months at a company before they move on.
It's complicated. We've just said, multi-physics, electrochemistry, you've got a lot of things going on. So there weren't really even, in fact, I don't think there are courses there isn't like a battery cell.
Not that I'm aware of.
Yeah, no. So you'd have to be, even the route into it is difficult. So it's a demand area. I mean, there's a lot of demand areas at the minute, don't get me wrong. So if you do electronics engineering or electrical machine design, power electronics, embedded software, I mean, a lot of these, for the same reasons or similar reasons, into new electronics, robotics, automotive, aerospace products, it's the way of the future. So, but batteries is... Yeah, what do you do? What do you study to be a battery engineer? What was your first degree in?
So mine was in mechanical engineering, but I was so surprised when I joined the research group here at Imperial, because yes, there was mechanical engineers in the mechanical engineering department, but there was also physicists, there was chemists, there was mathematicians, there were software developers. And the reality is to be a battery researcher or a battery engineer, you need to be you need to be very multi-physics. You need to be able to, solve complex math, but also understand chemistry and electrochemistry, and kind of physics, but then also the engineering principles of how you build that into a system. So it's a very, very challenging problem. And I went to a conference a couple of years ago, and there was somebody from Dassault Systems presenting. So Dassault Systems are the owners of products like SolidWorks, and they own CATIA as well. So a huge modeling company. And the guy presenting was saying that I think it was their CTO gave a speech a year before saying that how in his 40-year career in modeling, batteries were by far the most difficult problem he's ever came up against. There's so much still to learn, so much still to develop. And I guess that's what gets me out of bed in the morning, is every day still is a learning day. And I wish I understood batteries myself, but the reality is they're so complex that, I have a grasp high level. I kind of know what I don't know about them. There's so much still to learn.
That's a good place to be. I think there's unfortunately still come across people, it's a battery pack, throw it together. And I feel like the doomsayer, because I quite often find myself saying, if battery pack goes wrong, bad things happen. Like, you've got to engineer this properly. But the number of people who just don't. I mean, there's one of the big changes I'm quite excited about in the battery industry is new legislation that's potentially coming in, unfortunately, as a result of a lot of issues with cheap batteries in e-scooters and bikes and stuff like that. And, across Europe, and there's been issues in the US and in Asia as well. So I think governments have become aware that there's a bit of a problem with battery packs that aren't designed properly. And obviously the cell is the underpinning part of that, but then getting everything else right around it to protect it and make sure it does what you thought it was going to do is really hard, as people might appreciate from our conversation just now. So that's brilliant. I mean, I am in awe of what you've done. In 10 months, 4 or 5 customers, a team of, a dozen people or more. I mean, well done you. It's fantastic what you guys have done. So,
like I said, a lot of luck, Ryan. It's I find it hard to believe myself, honestly.
You wake up tomorrow back on the building site in Australia. That's probably taught you some good life lessons, that one. And probably a few new swear words that you didn't know before, I would imagine, as well. Fantastic. So it's been great to talk to you and record this episode. I hope people got something out of that and understand what you guys are doing and some of the complexities around battery cell development a bit more. So thank you very much for agreeing to come on.
No, honestly, thank you very much, Ryan. And if anybody's interested, please just follow us on LinkedIn. My co-founder Kieran's very good at keeping everybody up to date with what we're developing, and hopefully over the next few months we've got lots of exciting news to announce, and some educational materials as well for anybody that's interested in learning more about batteries.
Very good. So what we'll do for people, if you don't normally listen to the podcast, I will put links in the show notes. So if you expand the notes, you'll find links back to About Energy's webpage and Gavin's LinkedIn. We might even put Kieran's LinkedIn and the company one in there as well, and some of the other things we've talked about. And probably a link back to the original, the podcast a while ago with Greg Offer and some other things. But yeah, don't forget there is a huge back catalogue of episodes, so people can check those out as well. That would be great. So thank you. Thanks for taking the time out to join us today. And with that, we'll bring this episode